The universe is dying. Not today, not in a billion years, but dying nonetheless, with the quiet certainty of physics. It is a truth written into the very laws that govern every atom, every star, every galaxy spinning in the dark. From the smallest particle vibrating at the edge of existence to the last black hole smoldering alone in the void, everything that has ever been born will one day come to an end. Join us as we journey to the final chapter of the cosmos. We'll witness the slow extinction of stars, the evaporation of black holes, and the ultimate fate of time itself. And we'll ask the question that has haunted physicists for over a century: how does the universe end, and what, if anything, comes after? To understand how the universe ends, we first need to understand what the universe is doing right now. And the answer, it turns out, is both simple and staggering. It is expanding. Every second, the fabric of space stretches outward in every direction, carrying galaxies away from each other at speeds that grow with distance. You're well aware that this expansion was first confirmed by Edwin Hubble back in 1929, when he observed that distant galaxies were moving away from us, and the farther away they were, the faster they receded. But here is the part that changes everything. Back in 1998, astronomers Saul Perlmutter, Brian Schmidt, and Adam Rees were studying distant supernovae, expecting to find that the expansion of the universe was slowing down due to gravity. Instead, they found the opposite. The universe is not slowing, it is accelerating. Something is pushing space apart faster and faster with every passing moment. Scientists call this force dark energy, and according to our best measurements, dark energy makes up approximately 68.3% of everything that exists. Ordinary matter, everything you can see, touch, and measure, accounts for only 5%. The rest is dark matter, a mysterious, invisible substance that holds galaxies together but refuses to interact with light. So it turns out that the overwhelming majority of the universe is made of things we cannot see, cannot touch, and do not fully understand. And it is these invisible forces, dark energy in particular, that will determine exactly how and when the universe meets its end. But what kind of ending are we talking about? A sudden catastrophic collapse? A slow and silent freeze? Or something far stranger? Let's now take a closer look at the paths the universe could take and the science behind each one. Before we arrive at the end of everything, we have to witness the first great extinction, the death of the stars. Right now, the universe is alive with light. There are an estimated 2 trillion galaxies in the observable universe, each containing hundreds of billions of stars. Our own sun has been burning for approximately 4.6 billion years. It has roughly another 5 billion years of fuel remaining. When that fuel runs out, it will expand into a red giant, engulf the inner planets, and eventually collapse into a white dwarf, a cooling ember the size of Earth, radiating its remaining heat into the dark for billions of years more. But here is what most people don't realize. The era of star formation is already ending. Back in 2012, a team of astronomers studying galaxy surveys found that the rate at which new stars are being born across the universe has been falling steadily since it peaked roughly 10 billion years ago. In fact, the universe today is forming stars at only 3% of its peak rate. Slowly, inexorably, the cosmic furnaces are going out. It turns out that most of the stars that will ever exist have already been born. Astronomers estimate that stellar formation will effectively cease within the next 100 trillion years. After that, no new stars will ignite. The galaxies will begin to darken, one by one, as their remaining stars exhaust their fuel, collapse into white dwarfs, neutron stars, and black holes, and go cold. This period, the era after the last star has burned out, is called the degenerate era. It is a universe of darkness, populated only by the cold remnants of what was once brilliant. And yet, even in that darkness, something will still be happening. Something slow, something patient, something that even dead stars cannot escape. Let's zoom out from the death of individual stars and consider what this means for the universe as a whole. There is a concept in physics called entropy. It is, in the simplest terms, a measure of disorder. And the second law of thermodynamics tells us that in any closed system, and the universe is the ultimate closed system, entropy always increases. Order gives way to disorder. Structure gives way to randomness. Heat flows from hot to cold, never the other way. And over time, everything tends toward a state of maximum chaos and minimum energy. The inevitable destination of this process has a name. It is called the heat death of the universe, and it is, according to most physicists, the most likely ending of all. The idea was first formulated in the 19th century by the physicist Lord Kelvin, building on the work of Rudolf Clausius, but it is only in the last few decades, armed with data from satellites like the Planck spacecraft, that scientists have been able to map the true trajectory of cosmic entropy in detail. Here is what that trajectory tells us. As the universe expands and cools, energy becomes less and less useful. Stars burn out, black holes eventually evaporate, which we'll discuss shortly, particles decay, and after an almost incomprehensible span of time, the universe reaches a state of perfect, uniform temperature just barely above absolute zero, which is negative 459.67 degrees Fahrenheit, a temperature so cold that no energy can flow, no work can be done, no information can change. So the universe does not end with a bang. For most physicists, it ends in total, eternal stillness. Yes, we can say that the universe's final state is not death in the way we understand it. It is something quieter and in many ways more unsettling, a perfect equilibrium from which nothing can ever escape. This means that time itself, as a dimension that requires change to have meaning, effectively ceases to function. But before we reach that silence, the universe has several more chapters to go through, and the strangest one belongs to the most mysterious objects in the cosmos. Theory 1. The Big Freeze, the slow fade to nothing. The Big Freeze is the most widely accepted model of cosmic death, and it follows directly from what we know about dark energy and entropy. In this scenario, the universe continues its accelerating expansion forever. Galaxies drift apart until, in roughly 100 billion years, our local group, the Milky Way and its neighbors, is all that remains visible in our cosmic horizon. Beyond that boundary, all other galaxies will have receded faster than light can cross the gap between us. We will be cosmically alone. Then, the stars die. Then, even the cold remnants begin to decay. Protons themselves, the seemingly indestructible building blocks of matter, are theorized to decay over a timescale of at least 10 to the power of 34 years. After that, ordinary matter as we know it ceases to exist. What remains are black holes. Patient, massive, ancient black holes, orbiting each other in the dark across timescales that make our current universe seem like a fleeting moment. But even black holes are not immortal. In 1974, Stephen Hawking proposed that black holes slowly emit radiation, now called Hawking radiation, a consequence of quantum effects near the event horizon. Particle by particle, bit by bit, black holes evaporate. The last stellar mass black hole would vanish in roughly 10 to the power of 67 years. The last supermassive black hole in 10 to the power of 100 years. After that, silence. A vast, cold, uniform void. The Big Freeze. Not an explosion, not a collapse, just a universe that slowly runs out of things to do. However, the Big Freeze is not without its uncertainties. It assumes that dark energy remains constant, and that assumption may be wrong. Theory 2. The Big Rip, when space itself is torn apart. But what if dark energy is not constant? What if it grows stronger over time? That is the central idea of the Big Rip. In this model, dark energy does not merely accelerate the expansion of the universe, it accelerates its own acceleration. The force pushing space apart becomes increasingly violent until it overwhelms every other force in the universe, one by one. Imagine the universe as a fabric. At first, the stretching is gentle, barely noticeable, but then it intensifies. First, galaxy clusters are torn apart. Then individual galaxies dissolve. Then solar systems disintegrate as the expansion overpowers gravity. Then planets shatter. Then atoms themselves, held together by electromagnetic and nuclear forces, are ripped apart at the subatomic level. In the final fraction of a second, even the fabric of space-time is shredded into fragments. Physicists estimate that if dark energy is of the right type, what they call phantom energy, the Big Rip could occur in as little as 22 billion years from now. So what was there before the Big Rip? A universe that looked much like ours, only younger. What comes after? According to the math, the question may no longer have meaning. However, like all models of the far future, this theory is speculative. Can we measure dark energy precisely enough to know whether it is growing? That remains one of the most urgent open questions in cosmology today. Theory 3. The Big Crunch. The universe collapses back on itself. As always in science, there are competing theories, and one of the oldest imagines the universe not dying in a whisper, but in a roar. The Big Crunch. Imagine playing the Big Bang in reverse. In this scenario, the expansion of the universe eventually slows, halts, and reverses. Gravity reasserts itself, pulling all matter back together. Galaxies converge, stars collide, the temperature of the universe climbs as everything compresses back into a single, impossibly dense point. A singularity, mirroring the conditions of the very beginning. The Big Crunch was once the favored model among cosmologists. It has a certain elegant symmetry, the universe born from a point and returning to one. But the discovery of dark energy in 1998 dealt a serious blow to this scenario. If the expansion is accelerating, the universe will never reverse. The Big Crunch, at least in its classical form, seems unlikely given what we now know. Nevertheless, the Big Crunch refuses to disappear entirely because it contains a fascinating possibility. What if the crunch is not truly an ending? What if it is a transition? Theory 4. The Big Bounce, an eternal cycle. What if the universe does not end at all, but simply begins again? That is the proposal of the Big Bounce. In this model, the universe oscillates, expanding, contracting, collapsing to a point of extreme density, and then rebounding into a new Big Bang. Our current universe would be just one cycle in an infinite chain of cosmic rebirths. There was no first beginning. There will be no final end. Only the eternal rhythm of expansion and collapse. This idea draws on the emerging field of loop quantum cosmology, which suggests that at extremely small scales, quantum effects prevent true singularities from forming. Instead of collapsing to an infinite point, the universe compresses to a minimum size, then bounces. The laws of physics survive. A new universe emerges. So what will come after our universe ends? From the perspective of the Big Bounce, another universe, perhaps with different physical constants, different laws, different possibilities. And perhaps within that universe, billions of years from now, something will look up at its own night sky and ask the same questions we are asking tonight. However, this theory faces considerable challenges. We currently have no observational evidence of a previous cycle, and reconciling loop quantum cosmology with general relativity remains one of the deepest unsolved problems in physics. Theory 5. Vacuum decay, the most terrifying ending of all. But what if the universe ended not gradually, not cyclically, but suddenly, without warning, at the speed of light? This is the scenario of vacuum decay, and it may be the most unsettling idea in all of modern cosmology. You're well aware that quantum mechanics describes reality at its most fundamental level as a field of probabilities. In this framework, the universe currently exists in what physicists call a false vacuum, a state of energy that appears stable but may not be the lowest possible energy state. Think of a ball resting in a shallow dip on a hillside. It looks stable, but if the ball receives even the slightest nudge, it rolls down into a deeper valley below. In 2012, measurements of the Higgs boson at CERN suggested that the universe may indeed be in a metastable state, a false vacuum. If that is correct, then at any point, here or somewhere on the other side of the observable universe, a quantum fluctuation could trigger a phase transition. A bubble of true vacuum would form with entirely different physical constants. Inside that bubble, atoms cannot exist. Chemistry cannot occur, life is impossible. And the wall of this bubble expands outward at the speed of light, converting everything it touches into a new, alien form of reality. The key detail? We would never see it coming. The bubble travels at light speed. There is no warning. One moment, the universe is here. The next, it is simply different. Of course, vacuum decay remains highly speculative. Whether the universe truly sits in a false vacuum depends on precise measurements of the Higgs field that we are still working to refine. But the possibility alone has sent ripples through the physics community, because unlike all other theories of cosmic death, this one cannot be outrun, prepared for, or in any way anticipated. So, how does the universe end? In a nutshell, at this point, we don't know for certain. It may fade into eternal cold silence. It may be torn apart at the seams. It may collapse and be reborn. Or it may, without a moment's notice, become something else entirely. Each of these possibilities is rooted in real physics. Each is supported by brilliant minds who have dedicated their lives to the question. But perhaps the most remarkable thing is not the answer. It is the fact that we are here, on a small rock orbiting an ordinary star, with minds capable of even asking it. The universe gave rise to beings who can contemplate its own ending. And as long as we keep looking, keep questioning, and keep searching, in some small but meaningful way, the universe is still very much alive.